This video is to support students and possibly teachers who want to know a little bit more about the Physics, Earth and Space Science Standard 1.2. I've picked a phenomena that isn't likely to be used for your actual assessment. I really like this as a practice assessment because it's super quick to get all of the data, and then we can give feedback on what we're looking for in the assessment. So what I'm going to do is I'll run through two different investigations, both on the same phenomena, the brightness of a light bulb, and I'll go through experiment, data, graph for each of those, and then at the end I'll go through a bit of a discussion around what we're looking for achieved merit and excellence. I'll include timestamps so you can skip to the stuff that's relevant to you. I'm going to use Phyphox as my light meter for this experiment. Phyphox is a free app that you can get on your phone. It comes loaded with all sorts of cool features for investigating physics. And the one that I'm interested in today is the light meter.
So here's my table of results, and I've decided that I'm going to calculate the average illuminance. So when I'm doing that on the calculator, I'm keying in my three values and adding them together. And then I'm dividing, because there was three samples and I haven't removed any outliers, I'm dividing by 3 to get my answer for the average. One thing to be careful of is if I do the same calculation, but I try to do the division in the same step, then I get a different answer. And that's because according to bed mass, we're going to do the division first, and then we're adding the other two values to that. So that's something that you've got to be careful with when you're working out your averages. Okay, so my average for this one was 1835. I'll round that because the next number afterwards is a 0.6 there. I'll round it up to 134. One common sense check when you're doing your averages is that the average value should always lie somewhere between the lowest and highest value in the data set. So I know that if I worked out an average here and it was below 131 or above 135, I know that I'd made a mistake. Okay, so I've now calculated some average illuminance in lux, and we should be able to see from the table that the relationship is that as the distance from the light bulb increases, then the average illuminance decreases. So for my independent variable, which needs to go up to 2.4, then I can see along this side of my graph here, if I go 0, 1, 2, 2.4, then that's going to use up a good portion of the graph paper. And then for 2000 on my dependent variable, so looking at 0, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 big boxes. And so I'll probably do for 2000, I'll do every 5 big boxes is going to be 1000. So that'll get me up to 2000 right at the top of the graph. So using almost all of the graph paper. So I'll go ahead and do that. So then I'm plotting my points. I'm going to be plotting my average value, so 0.4 and around about 1800, just over. So 0.4, that's going to be my 0.5. So 0.4 will be here along this line. And then 1835, 1800 would be here. Now, if I've got 5 boxes for a jump of 200 from 1800 to 2000, then each little box is going to be about 40. And so my 1835 value is going to be just below this line here. So I'll find that's my 0.4 on the x-axis, and then put my mark around about there. So my next value is 0.8 and 556. So 0.8 and 500. So 0.8 being about here. And then I've got 200, 400. That's going to be 600. So now my 500 is going to be about in the middle there. And then each little box we said was 40 on this axis. And so if I need 60, I need about a box and a half. So my 556 would be just a touch below that line there. My next value is 1.2 and 273. So 1.2 is here, and then 273. Well, there's my 200. And again, each little box is 40, so it's 273 is just a little bit below 280. So it's going to be around about there. 1.6 and 161. Probably not going to worry too much about the 1 on the graph. So 1.6 would be here, and 161 would be 4 boxes there. Then 2.0 meters and 134 lux. So 2.0, 134. 3 boxes would be 120, so it's going to be a little bit, not quite halfway up the next box, but a little bit up the next box. And then 2.4 and 94, so 2.4 is here, and 94 is just going to be below that, the second little box. And so that would be my graph. If I wanted to show a trend, I wouldn't join the dots. I'd normally try and show like a smooth curve to indicate the trend. So something like that. There's a wee bit of a wobble there. I'm not too worried about that, but that's showing the trend or pattern in my data. So for this investigation, we're going to keep the light meter a fixed distance away from a light source, and we're just going to vary the voltage of the supply and record our readings. So we should be able to get data really quickly and efficiently. I've put a bit of plasticine over the switch because that lights up when it's switched on. And I'll run through and take some repeats. The angle that the light meter is at relative to the light can make quite a big difference. So, any results that don't sit in a specific pattern with the others might be because the angle of the light meter changed or something got in the way of the light meter. It's normally pretty consistent. Okay, so for our second investigation, this is where we increased the voltage, kept the light meter a fixed distance away, 30 centimeters in my case, and then measured the illuminance. The voltage is my independent variable, that's the thing I deliberately changed, and the dependent variable was the illuminance. When I sketch a quick graph of what I think it's going to look like, I can see that the voltage increases in even jumps, but the average illuminance increases a little bit at first, and then more, and then more, and then more, and more. And so that's probably going to give us a shape of a graph that's something like this. Voltage, again, my independent variable on the x-axis, illuminance, my dependent variable on the y-axis. And so when I draw my graph of that one, I've got it laid out like so. I had 7 big boxes along this axis, and I had 10 big boxes along here. I know that my voltage needs to go up to 12, so with 7 boxes, that's easy jumps of 2 to get me up to 12. Easy jumps of 2 to get me up to 12 there. And then on the on the y-axis, I need to get up to at least 227, probably about 250. So with 10 boxes, 250 divided by 10 gives me 25 jumps of 25. I don't need to mark that every 25 on my scale. I can go 50, 100, 150, 200, but I do need to be consistent with those jumps. And then plot my points, and I've drawn an approximate line of best fit. It's a little bit wobbly, but yeah, I'd expect you'd be more likely to be dealing with a linear relationship, so I'm just showing you the sort of graphing skills that you might need for your assessment.
So here's the criteria for achieved merit and excellence according to the standard. For achieved, we need to describe relevant physics concepts. That's plural, so there's got to be at least 2 concepts described. And we need to describe the relationships involved in a physical phenomenon using evidence. Then for merit, we're explaining how the concepts and the relationships are involved in the phenomenon, in this case a bulb. Note that it doesn't need to be, if you're doing 2 investigations, you don't need to get 1 concept from each investigation. You could explain 2 concepts from 1 investigation and none from the other, and that would be okay. The relationships should be connecting your independent and dependent variable. And for merit, it needs to use processed evidence. So that might be averages, might be tables, might be graphs. It might be other calculations that have been performed. And for excellence, we're looking to integrate processed evidence with a discussion of the relevant physics concepts and relationships involved. So here's a bare minimum achieved statement. For our concept, the light radiates outwards from a source. For our relationship, the illuminance decreases the further you go from the bulb. We need to include evidence, and so I've used some of my raw data, because for achieved you don't need to have processed it, so I'm just making that clear. At the shortest distance of 0.4 meters, the illuminance was 1917 lux. At the highest recorded distance of 2.4 meters, the illuminance was 92 lux. And then for our second investigation, at higher voltage, the bulb is brighter and a higher illuminance is seen. So I think we've got the concept described and the relationship described there. Backed up with evidence. For example, at 0.30 meters, 0 lux was recorded at 2 volts, but 12 volts produced 234 lux. Okay, so here's our merit and excellence response for the assessment. It builds on what we've said for the achieved already, but the important thing to note for merit is that we're explaining how the concepts and the relationships are involved in the phenomenon, in this case a bulb. And we're drawing on processed evidence. So for this example, I've used the averages, but that evidence could come from your tables or your graphs, as you've seen earlier. So the explanation for the first investigation: the further you are from a source, the more the energy has spread out from that source, and so the energy measured at a more distant point would be less. For the second investigation, at higher voltage, the bulb is converting more electrical energy into light energy every second, and so the higher the voltage, the greater the rate of light energy produced, and the higher the measured illuminance at a fixed distance. So with that statement, we've explained how the concept relates to the phenomenon, and then the next sentence draws on processed evidence. Now for excellence, you've kind of got to bring the ideas together, and integrating processed evidence in a discussion of both the concepts and the relationships. So to try and make that clear here, what I've done is in the final paragraph, I've tried to bring both the ideas together with the processed evidence, which, along with the paragraphs above, would be sufficient for an overall excellence. So either bringing the light meter closer to a light source and then processed evidence, or increasing the voltage of the light source would increase the recorded illuminance. So we're seeing how both of those relationships and concepts fit together with processed evidence. Going further from the bulb or decreasing the voltage would decrease the illuminance measured. All right, I hope that's been helpful for you. Feel free to leave any questions or comments. Thank you.